Hello everyone, welcome to the second tutorial of the vibrations. Today we will be working on equivalent spring constant, which is very important for simplifying the system and solving the vibration problem. So let's begin. Okay, so as a review, I want to show you different methods that we can quickly use for finding the equivalent spring constant of a system. So the first method is when we have a parallel or series connection of springs. For example, if we have a parallel connection, like for example we have one spring and the other spring, so say for example K1 and K2, and they are connected together and a force is applied to them, then the equivalent stiffness or spring constant would be the summation of them. So K EQ equals to K1 plus K2. Same as capacitors basically in electricity. So you can use the same analogy for finding equivalent springness or stiffness of parallel connections. So the other types of connection is basically the series connection. So when we have a series connection of springs, we have for example 1 and 2 springs, or even we have more, right? So we have K1, K2 and K3 and the force is applied to them. Then you can have 1 over K equal to 1 over K1 plus 1 over K2 plus 1 over K3. So you can simplify these fractions and find K equal. In fact, for parallel connection, the deflection is equal for all springs, but for the series connection, the force is equal for all springs. So we can use the Newton's law or the Hooke's law to find equivalent stiffness. So these are the two common types of connections of springs. And in many other spring connections, you have to make sure how to geometrically relate their deflection, and then you can find the equivalent stiffness using Newton's law. The other common method to find the spring constant is based on the potential energy. So I would say potential energy method. In fact, for finding the equivalent spring constant, you can suppose that the equivalent potential energy, which belongs to the equivalent stiffness, is equal to the summation of the potential energy of each spring. So if we have infinite springs, we can use that. So it means that we can have 1 over 2K equal X equal squared. So as you know, this is the potential energy for a spring. 1 over 2kx squared is equal to 1 over 2 K1 x1 squared plus 1 over 2 K2 x2 squared, and so on, right? So if you have multiple springs, you can find the deflection of each and then add the summation and set it equal to the potential energy related to the equivalent stiffness, and then simplify to find K equal. So this is also a very common method to find the spring constant, especially when we have the combination of linear and torsional systems. So again, same analogy for torsional systems. We can have parallel connections and series connections of torsional systems. For parallel connection, you have equal amount of torque applied to the springs, but for series, we have equal amount of angle of rotation to the springs, right? So let's have a couple of examples and see how we can use these methods to find equivalent stiffness, okay? So this is the first example we have for today, which we want to find basically the equivalent stiffness of the system as the problem statement says. So as you can see here, we have multiple connections. We have series connections and parallel connections, and we want to find the overall equivalent spring constant of the system. Okay, let's look at this system and see what we have. As you see, we have two springs, K1 and K1, and they are equal in terms of the magnitude of the spring constant. They are connected in parallel. So these two are connected in parallel, and the equivalent stiffness for these two is 2K1, right? So we have 2K1 here, right? Same thing here, we have K3 and K3, so these two give us 2K3. Now I want to rewrite or redraw the system and see what we have in here. So if we use 2K1 here instead of the two parallel springs on top, then we have K2 here, right, from here, and then we have this one as 2K3, right? Again, we have two parallel springs, K3 and K3, so the equivalent for these two is 2 times K3 because they have equal spring constant, right? And then we have a big spring here, K4, and they are in parallel to each other. And finally we have K5 here, okay, and this is the force. So as you see, we simplified our system to some extent, but we need to work on the system again and again. So as you look at this picture, you can see that we have these 3 springs in series connection. So as you see, we cannot simply add them up to K4, so we have to somehow find the equivalent spring constant for these 3 and then add it up to K4 because it will be basically in parallel connection. So imagine these 3 has an equivalent stiffness of KE1. So I'm going to use KE1 for these 3, and I'm going to make the system as this. We have K4 and KE1, and then they are connected to K5. Okay, so we need to find KE1, and then we can continue on the modeling of or finding the equivalent stiffness of the system. So what is KE1? Look at these 3 springs on the left hand side. We have 2K1, K2, and 2K3. So we can use the series connection formula, right? Let's see what we have. So we have 1 over KE1 equals to 1 over 2K1 plus 1 over K2 plus 1 over 2K3. I hope you can remember these 3 terms, right? So we have 2K1 and 2K3, and all these 3 are connected in series connection. So if we simplify for KE1, we just need to simplify these fractions and use some mathematical rules. We get KE1 equals to 2K1 K2 K3 divided by K2K1 or K2K3 plus 2K1 K3 plus K1 K2. Right? Now the system is simpler and we can draw it as this. We have KE1 and then we can use K4, so we don't have to use E here. So we have basically K4 and then we have K5, right? So now we have 2 springs on top which are connected in parallel, which makes it easier for us. So these 2, we're gonna use KE2 instead. So we get this system, right? We have KE2 and K5. So what is KE2? Very simple, right? KE2 is K4 plus KE1, right? Because they are connected in parallel. So after that, we have 2 springs in series, right? So the overall spring constant or equivalent constant from these 2 would be 1 over KEQ, which is equal to 1 over K5 plus 1 over KE2. So from that we can find the overall or the final, this is the final spring constant, right? That's it. This is what we are looking for, the equivalent spring constant. So let's see what we have here. Okay, so we ended up to this. Let me go back. So we ended up to this and K5. So we have K5 here and KE2. And you remember KE2 from before? So 1 over K equal, where K equal is our final spring constant or equivalent spring constant, is 1 over K5 plus 1 over KE2. And we already know the expression for KE2. So simply K equal is equal to basically KE2 times K5 divided by K5 plus KE2. So what we need to do, we have to substitute the expressions for KE2. And you remember KE2 was also a function of K4 and KE1. So if we do this, I just want to show the expanded version of the equivalent spring constant, and I hope you can find it yourself as well. So these two will be, but finally, let me use another color. We have for these two systems ended up to this. So we only have one spring and the stiffness is KEQ. And KEQ has a very large expression. I hope I can fit it in there. So we have K2, K3, K4, K5 plus 2, K1, K3, K4, K5. You can double check my answers if you want. Plus K1, K2, K4, K5, and finally plus 2, K1, K2, K3, and K5, right? And in the bottom we have K2, K3, K5 plus K2, K3, K4 plus 2, K1, K3, K4 plus 2. I know it's pretty lengthy, but this is the final answer for our system, and you can double check if you want. Plus K1, K2, K4. This is K4 and this is K1, and we also have more terms. I continue here in the denominator, plus K1, K3, K5, and plus 2, K1, K2, and K3. So the whole thing is the denominator, so I'm gonna use brackets to not confuse. So this is the whole denominator. So as you see, we will be able to find the equivalent stiffness or spring constant, and the whole system became like this. Why it is important? So imagine there is a mass connected to this end and we have a vibration, and you want to simplify it to only one mass and spring system, right? That's how we can find the equivalent stiffness. Okay, so let's go to the other example and see how we can find the equivalent stiffness or spring constant of the system. Okay, so this is the next example, which we are going to combine both the series and parallel connection formula and the energy method to find the equivalent spring constant. So as you see here, in this system we have a combination of torsional springs and basically linear springs. So how it works, so let's see what we have here. We have a disk with a moment of inertia of, say for example, J. So J, which is under a torsion, and theta is the degree of freedom. So as you see, we have two linear springs. Why linear? Because the torsion, or say a small rotation of J or the disk, will make the two springs of K5 and K6 to expand and compress. respectively, right? At the same time, because of the rotation, we have K4, K3, and K2 and K1 under a sort of torsional motion, which means that the shaft has a sort of a springless behavior, but the type of springless is a torsional springless, right? So generally speaking, when we have a shaft, right, and the shaft is under a torsion, and we know that the shaft has a moment of inertia and a shear, like a stiffness, Kt, the torsional stiffness is Gj over L. This J is different from here. This J here is basically our disc moment of inertia, but the J here is the cross-section moment of inertia of a shaft, right? So L is the length and G is the shear modulus, right? So for now, let's see what we have here. So as you see, if we look at these K1, K2, and K3, so I'm gonna look at them separately. So just focus on K1, K2, and K3. If we have a virtual rotation here, what happens is same amount of torsion is applied to these three shafts, right? So what happens is, if I want to draw it again, so forget about the other components. So we have one shaft, another shaft, and the third shaft, and they have different cross section or maybe even different materials, so their stiffness are not necessarily equal. So what happens is, if we have a sort of rotation in the system like this, the shaft, looking at the pin or clamped point, undergoes the overall angle of rotation, and as you see, the torque is equal for each one, right? It means that we have a sort of series connection. Why? Because the total rotation angle is the summation of the rotation of each shaft. So we have a series connection in a torsional fashion, right? However, if we look at a disc, a shaft is on top and another shaft is on bottom, and then we have a rotation. As you see, same amount of rotation is applied to the top one and to the bottom one, right? But the torque is somehow distributed between them, right? So this shows a parallel connection, right? For now, let's forget about other components. Okay, with these considerations, let's see what we have and how we can simplify the system. Okay, so let's look at these three shafts, K1, K2, and K3. So K1, K2, and K3 are in series connection. So I'm gonna, instead of them, use KT1. KT1 is the equivalent springness of K1, K2, and K3. And how we can find it? The series connection formula. We have 1 over KT1 equals to 1 over K1 plus 1 over K2 plus 1 over K3. So after the simplification of this, we can simplify KT1. Now, with these assumptions, let's see how the system look like. So I'm gonna simplify the system to this shape. So we have the disc, we have KT1 in the bottom, which is the equivalent stiffness of K1, K2, and K3, and on top we have K4, right? And we have for sure the two linear springs that we are gonna use them in the future. We're not gonna touch them for now. So what we have here, we have KT1 and KT4 as two parallel springs in the torsional fashion. So instead of these two, we can have KT2, for example. So what is KT2? So KT2 is the equivalent for KT1 and K4. So because the system is in parallel connection, we have KT1 plus K4. That's it, right? So the overall system will be simplified to this shape. So we have the disc. I'm gonna enlarge it, and then we can put it on top or bottom, doesn't matter. And we have this torsional spring with the constant of KT2. And what is KT2? KT2 is in here, right? The summation of KT1 and K4. And what is KT1? It's over here. That's it. And now we have the two linear springs, K5 and K6, which we will work on them in the next slide. Okay, so in fact this is K6. So let's do that. So as you may remember, we ended up to this system. So we have the disk. Let me go back here. We have the disk with the moment of inertia of J, and then we have the equivalent stiffness for all shafts, which was JT2, and now we have the two linear springs on the side, right? So we have K5 and K6. Okay, so let's look at this disk from the top view or the bottom view, doesn't matter, and we forget about KT2 for now, to see what happens for K5 and K6. So if we draw it again from the top view, as I said, so this is the center. So as you remember, this is theta. So let's see what happens. So we have the first spring here, K5, and we have K6 here, right? So let's see what happens if we have a sort of rotation on the system. So this is the original position, and we are gonna give a sort of virtual rotation in the direction of theta to the system. So what happens is the system becomes like this, and normally for vibration systems, we suppose that the amount of rotation or vibration is small. So this amount of theta vibration, so this point from there comes here, so the spring sort of expanded like this, right? Sorry, my drawing is not very nice, so I'm gonna use again. That's it, and the other one goes here. So as you see, the spring on the left hand side expanded for this length, so let me use another color, and for the other side it was like nearly compressed for this amount. And what is this amount? It is r theta. And what is r? R is basically the diameter, or sorry, the radius of the disk. So we can suppose that the deflection of K5 and K6 is r theta, right? This is just a simplification. So let me write again. So we have r theta, right? So if we have the torsion of theta on the system, K6 has the delta 6, which is equal to r theta, and K5 has delta 5, which is equal to r theta. So how can we combine them, or how can we find the equivalent stiffness based on these considerations? We have to use the other method, or the potential energy. And remember, the problem statement is looking for the equivalent torsional spring constant, not the equivalent linear spring constant. So for that case, we should write, or let's say U equal the potential energy of the like the equivalent spring is equal to the potential energy of the springs in the system. What do we have here? We have U5, which belongs to K5. We have U6, which belongs to K6. And finally, we have UT2, which belongs to KT2, right? Don't forget that. Okay, so let's see what we have here. So we ended up to this expression, U is equal to U5 plus U6 plus UT2, right? So let's figure out the potential terms or potential energy components for this function or this expression. For an equivalent torsional system, we know that U equal 1 is 1 over 2 K equal theta squared. So remember, the potential energy for a linear system or a linear spring was 1 over 2 K x squared. For a torsional system is 1 over 2 K theta squared, where K in this case is a torsional spring constant. So for U5, which was a linear system, we have 1 over 2 K5 delta 5 squared, where delta is the deflection of a spring K5. Plus, same thing for U6 or for K6, which is K6 delta 6 squared. And for UT2, which is a torsional system or a torsional spring, is equal to 1 over 2 K T2 theta squared. Right? But as you may remember, for delta 5 and delta 6, we found an expression as a function of theta, right? So we have 1 over 2 K equal theta squared is equal to 1 over 2 K5. What was delta 5? It was R theta and then squared, plus 1 over 2 K6 R theta squared. Why? Because delta 6 was R theta, plus the term we have for the shafts, 1 over 2 K T2 delta squared. As you can see, for all the terms here, we have theta as the variable of the system, so we can factor it out and simplify. So as you see here, we have 1 over 2 in all, which we can cancel them out from all the sides of the equation, and we have theta squared here, right? So let me use another color and see how we can simplify it. So we have theta squared here, another theta squared, and theta squared. So if we simplify for K equal or the final equivalent stiffness of the system, we can find that as K equal to R squared K5 plus K6 plus KT2. And that's it. We found the equivalent stiffness of the system, which is a torsional spring constant. And you might be asking why we have R squared here, and if it makes sense. Yeah, because K5 and K6 are linear spring constant. And if we look at the dimension and how it should be valid, it has to be multiplied by a meter squared or something. So in fact, we will be able to find the final equivalent torsional spring constant of the system, combining the series and parallel connection formula and the energy method. I hope you got the idea of finding the equivalent spring constant of the systems that is very actually useful for analyzing the vibration of systems when we have multiple springs that are somehow connected to each other or their deflection is somehow related to each other. Thank you and stay tuned for the next videos.